Okay, let's just dive right into this. It's kind of a funny paradox in the AI world, isn't it? We can build these massive models that effortlessly crush human grandmasters at chess, but you ask a multi-million-dollar robotic arm to rummage through a messy bin of socks, and well, it completely freezes. Grasping an isolated object on a pristine, well-lit table, yeah, that's a solved problem. But as the e-commerce logistics industry absolutely explodes, high-density warehousing has become the new frontier, and man, it is an entirely different beast. So for today's explainer, we're looking at a massive breakthrough in AI spatial reasoning that completely flips how robots understand their chaotic physical environments.
I want you to picture this for a second. Imagine a robotic arm equipped with a rigid, extended tool, like a blade. Its goal is to insert this blade into a fabric bin to stow an item. But the bin isn't empty. It's packed, highly cluttered with random, shifting objects. The robot literally has to actively sweep items aside just to create a pocket of insertion space. So how does a robot's mind actually compute where it's safe to push without crushing the goods?
Here's our roadmap to figure that out. 1. The cluttered challenge. 2. The problem with pose. 3. The VulcanVoxel architecture. 4. Masked autoencoders. 5. Benchmarks. And 6. Production stacks.
Starting with Section 1, the cluttered challenge. Let's lay out the true physical difficulty of high-density warehouse stowing. In real-world logistics, production stow systems generate millions upon millions of manipulation episodes every single day. The robot is constantly facing novel, messy, unpredictable scenarios, so finding that perfect insertion space for a tool remains a massive headache. And, in logistics, time is quite literally money. If a robot takes just 5 extra seconds to calculate a safe path, and you multiply that delay across millions of cycles, that costs a warehouse millions of dollars in lost throughput. You aren't just looking for an empty spot, you're looking for an affordance, a volume of free space where the tool can safely navigate and manipulate its surroundings.
Moving to Section 2, the problem with pose.
So why are current state-of-the-art AI planners struggling so hard with this? Well, traditionally, developers have treated affordance discovery as a parameter space problem. They use SE3 pose distributions, essentially trying to predict the exact X, Y, Z coordinates and rotations the robot should take. Contrast that with 3D occupancy fields, which rely on spatial reasoning. Think about it like this. Predicting an SC3 pose is like trying to navigate a pitch-black, messy room by memorizing the exact footsteps of someone who successfully walked to the door before you. It works perfectly, right up until a chair gets moved into your path. At that point, you fail completely. 3D occupancy fields, on the other hand, are like just turning on the lights and looking at the whole room to find any open path. SE3 parameters carry literally no inherent structure for reasoning about whether an unobserved placement is actually feasible.
And this brings us right to a fatal flaw in current models: unimodal bias. Unimodal bias happens when a manipulation policy executes a successful stow cycle in training, and standard generative objectives, like your typical diffusion models, learn to faithfully imitate that exact trajectory. They're optimizing for policy imitation rather than geometric validity. So when the robot is operating in a cluttered bin in the real world, and its preferred memorized pose is blocked, it just freezes. It can't recover alternative geometric paths because it collapsed multiple valid insertion possibilities into a single unimodal distribution. It literally doesn't know how to adapt.
Which leads us to Section 3, the VulcanVoxel architecture.
But what if we ask the geometric question in the right domain? This brings us to a massive paradigm shift presented in the arXiv paper 2607-0549, the VulcanVoxel architecture. VulcanVoxel's core philosophy is that blade affordances are not coordinate points at all. They are spatial objects. They're subsets of 3D space defined strictly by geometric feasibility. By shifting to this mindset, VulcanVoxel completely bypasses labeled pose distributions. Instead, it computes feasibility locally at each individual voxel within the 3D space. If you're newer to the terminology, just think of a voxel like a 3D pixel in a video game. It outputs a continuous feasibility map, totally wiping out the sampling overhead that constantly plagues those traditional pose-based planners.
On to Section 4, masked autoencoders. Let's unpack the technical engine that actually makes this possible. To keep inference strictly spatial, the VulcanVoxel system applies a masked autoencoder directly over a 3D occupancy field. It happens in 3 distinct steps. First, the mechanism randomly masks portions of the occupancy grid. Second, it trains the neural network to reconstruct the spatial footprint of the blade, strictly conditioned on the geometry of the surrounding scene. And third, during inference, it evaluates every single voxel independently to output a voxel-wise feasibility map.
Planners can then just extract contiguous volumes of free space that satisfy the robot's physical constraints.
By utilizing spatial masking, the network is forced to learn local geometric relationships instead of just memorizing global pose correlations. This completely avoids that unimodal bias trap we talked about earlier. Honestly, this is considered a bit of a holy grail in AI because it represents actual reasoning, not just rote memorization. Even if the training data only showed one way to insert the blade, the spatial representation naturally understands the geometric constraints of the whole bin. This allows the robot to discover brand new multimodal insertion paths on the fly, dynamically adapting to whatever chaos is in front of it.
Section 5. Benchmarks.
Let's look at the hard data, because, in robotics, a beautiful theory means absolutely nothing if it doesn't execute accurately and rapidly in the physical world. The VulcanVoxel architecture was trained on 10,000 real warehouse stow episodes. And here's the truly exciting part. It was done entirely without human annotation. Think about the massive labor savings that represents. This drastically lowers the cost and time barrier required to train warehouse robotics, making it a huge leap forward for unsupervised learning in these highly complex environments.
When put to the test, the real-world impact is pretty striking. The best pose-based baseline models tap out at a 0.71 top 5 coverage score. VulcanVoxel pushes that success rate to an incredible 0.89. This data directly confirms that switching to a continuous spatial representation absolutely translates to significantly higher success rates when a robot is actively fighting against dense, unpredictable clutter.
But what about speed? The base voxel-to-voxel architecture processes the full field in about 1.4 seconds. While impressive, the researchers took it a step further. They created a distilled student model for RGB to voxel inference, and its speed is blistering, 30 milliseconds. To put that into perspective, a human eye blink takes about 100 to 150 milliseconds. That means this robotic system is calculating the feasibility of the entire 3D space 3 to 5 times faster than you can even blink. This proves for sure that deep spatial reasoning doesn't require heavy, sluggish transformer backbones, and it easily fits into standard 100 millisecond control frequencies for real-time updates.
Finally, Section 6. Deploying in production stacks.
Now, for the developers and engineers tuning in, let's talk about taking this out of the lab and deploying it into your actual production manipulation stacks. Here are your rapid-fire deployment rules based on this research. First, stop relying on standard diffusion objectives for cluttered affordances. Shift to voxel-based spatial reasoning. Second, structure your planning loops to query the voxel map at the exact start of each cycle. Third, ensure you filter the output grid strictly through your blade's specific collision envelope to extract valid trajectories. And finally, a massive warning to keep in mind. Pin your occupancy grid resolution and mask configuration to exactly match your training conditions. If you have mismatched voxel sizes, your accuracy will degrade immediately and you will completely break that distilled model's 30 millisecond latency guarantee.
If you want to benchmark this on your own edge hardware, or maybe just validate the voxel reconstruction quality yourself, the authors have actually open-sourced a dataset of real blade insertion cycles. You can find it right at the ARM bench link displayed here, along with a full archive paper at 2607.02549. It is fully compatible with spatial planning pipelines, complete with all the necessary RGBD observations.
So, we've seen how treating affordances as spatial objects instead of geometric coordinates brilliantly solves the unimodal bias problem. We've explored the massive leap to an 89 success rate and those mind-bending 30 millisecond inference speeds. Which leaves us with one critical question to ponder today. As warehouses get denser and robotic autonomy becomes even more fundamental to global logistics, is this the end for pose-centric robotic planning? Thank you so much for joining me for this explainer. Keep building, keep learning, and I'll see you in the next one.